I'm Melissa.
I'm Jam.
And I'm a chemist.
And I'm not.
And welcome to Chemistry for Your Life.
The podcast helps you understand the chemistry of your everyday life.
Okay, Jam, I'm very excited for today's episode.
Really? That's weird. That's like kind of different than normal.
I know. I'm so excited about everything. But this one I am extra super excited about.
I would love for there to be a time where we start an episode and you say, okay, Jam, I'm not excited about today's episode at all. And
well, that's kind of how I felt about plastic. It was a little heartbreaking.
That's true.
But
that's
interesting.
True. And important to share about.
Yes.
You know, so like you can be excited about telling everyone about something that's important for them to know without being excited about the fact that it is true.
That it is terrible.
Yeah.
Yeah, that's true. Well, maybe sometimes I'll say this. Sometimes when I'm preparing to write an episode and I can't think of an idea that I'm excited about, then I'm not excited. Then I'm like, ugh, and I don't want to do any of these topics. And then I get excited about one. So that's why I'm always excited about it.
Right. It's the one that you got excited about this past week.
Right. Okay. Exactly.
Got it. Okay. So what is it?
Okay. It is from listener. And actually this person is a real life friend of ours.
Okay.
Katie J.
Okay.
She wrote in and asked about how Pop Rocks pop.
Oh, nice. The candy from old.
Uh-huh.
I mean, that probably still exists, but I've not, had Pop Rocks in who knows how long.
Well, I think we're going to have to do a little Pop Rocks experiment or something because
Absolutely.
It does still exist. And it's a really super fun question, and the answer is so chemistry-y.
That sounds like it would have to be.
Yeah.
If not, then I would be like, okay, it must just be magic then. In that
but
case.
It is not a chemical reaction, actually. It's chemicals doing things. Obviously, everything is kind of, but it's not a reaction.
Okay.
So Pop Rocks were invented by a tag team of two chemists, according to the Pop Rocks website.
Okay.
Initially, it was invented by someone attempting to make an instant soda, like Coca-Cola in a tablet, I think, was the idea.
Okay, like add this to some water and it'll become a soda.
Right.
Okay, interesting.
But it didn't really work out, so it kind of got abandoned.
Okay.
And then 20 years later, another chemist came along, saw the potential for this as a candy, and slightly modified it to make it usable. And that's how Pop Rocks were born.
Interesting. Wow. I would not have expected that.
I know. Huh. I was very excited to see it on the website attributed to chemists because I think food chemists do a lot of things behind the scenes. But for it to just get the credit, a chemist did this. So that was exciting to me.
That is exciting. Huh.
So what Pop Rocks are is essentially carbonated candy.
Carbonated candy. So it's carbon dioxide?
Yes.
Okay.
It's highly pressurized carbon dioxide in a hard candy shell.
Interesting. Huh.
So I want to talk about what highly pressurized carbon dioxide actually means.
Okay.
So I think we think about things being under higher pressure, if your air pressure in your tire is low versus if it's high. But what it actually means is if you have a higher concentration of gaseous molecules in a space than less concentration of gaseous molecules, they will move around more and exert more pressure on the container they're in.
Okay. Because
gaseous molecules are moving around and they are trying to be further apart from one another.
Right.
So you may have heard this from Andy on Parks and Rec. He says, in a shocking move, that gases expand to fill the size of the container they're in, which is like very surprising from him because he kind of is usually saying goofy stuff.
And also, doesn't he say it in a really random time? Like it's not even relevant or something like that?
I think it's because somebody has a poison-filled balloon, April.
Oh, okay.
And he said no, because if there was poison in one of these balloons, it would expand to fill the size of the container we're in or something like that. So these gases are moving around. They're trying to spread out. But if there is a high concentration of them and they can't spread out, they'll be under pressure, basically. They're putting pressure on the container, and you need the pressure to contain them back.
Got it.
The way I think of it, I don't know why this came to my mind, is if you think of a high pressure situation, it's similar to having a fish net full of fish, like in that Finding Nemo part.
Oh, yeah. Where they all swim down.
Yes, there's tons of fish in the area, and they're all trying to break out. But they can't really. But there's so many in there that they're really exerting pressure on the net.
Right. Okay. Yeah, it's a great analogy.
But normal air is like a fish net with not very much. Like the air that we're in right now is mostly empty space with a few molecules around. So inside your Pop Rocks are little bubbles inside the hard candy shell with highly concentrated CO2 in them.
Okay, interesting.
So that's known as pressurized carbon dioxide bubbles.
Yeah.
So a high concentration of CO2 in a smaller space than you normally have.
Okay.
Okay, so as soon as the fish net gets removed, the fish are going to scatter, right?
Right.
Okay, so that is essentially what happens when you have the Pop Rocks in your mouth. They're in this container that's holding all the CO2 in.
Right.
But as you put it in your mouth and the sugar starts to break down, eventually the pressure that the molecules are putting on the container to try to get out is going to be greater than the gradually thinning, smaller sugar wall. And eventually the molecules will be able to break out as if the fish tank popped open or the fish net popped open.
Right. So that's why it feels like a pop.
Yes.
Okay. Because they're able to, at a certain point, overcome the strength of the walls that are kind of holding them in, and they do kind of pop out.
Yes.
But it is just a gas that was trapped in there.
Yes, it's a gas that was trapped in there that gets its opportunity to rapidly expand to fill the size of the container. In this case, your mouth, or if you open your mouth, the whole atmosphere.
Yeah. Interesting. So if you held your mouth closed while you had Pop Rocks in there, would your like kind of cheeks puff up a little bit, you think? Or was it not enough to do that?
It might. I don't know.
I've never tried that before.
You'd have to keep your mouth closed the whole time. But also, I don't think your mouth is a closed system.
That's right. Yeah. You have to breathe the whole time. So you'd be you'd have to let it out.
Yeah. But there also was some fear that it could choke children for that reason. But really, that's not possible. The worst that could happen is you'd get like gas in your tummy.
Yeah. Right.
Is what it seems like they're considered safe.
When people measure like different amounts of pressure for like gases and stuff, I've heard just in like, I guess, TV shows and books and stuff, because I like sci-fi things, they'll use the word like atmosphere.
Yes.
Do they mean that almost as like a word to describe what would be a normal amount of pressure if you just measured like outside on
pretty
Earth,
much.
basically? It's
just another unit of measurement for pressure. So there's like, I don't remember what the other one is because I feel like I used atmosphere most often. But atmosphere is a unit of pressure, and it's actually not the same everywhere outside. I think it's at sea level.
Oh, I see.
The amount of pressure that is exerted just by literally the atmosphere. So you would need like 4 atmospheres to be under greater pressure or whatever. So it's a unit of measurement, almost like a mile, or a pound. It's like this amount of pressure is equal to an atmosphere.
Yeah.
And you can convert that. We didn't do that. We don't use that very much in OChem, but in Gen Chem, you'll use that to solve problems, especially about gas molecules, and figure out how much pressure and how many molecules would give you this temperature, things like that.
Got it. Is there another more like chemistry related unit to measure pressure that's not atmospheres, or is that the standard?
I definitely use atmospheres a lot. I think I just had that. There's a constant that you use in gas equations, and you can have it in a bunch of different units. And I had the atmosphere one memorized, so I'd use that the most.
Got it.
But there's also PSI, and I think the SI unit is maybe pascals.
Okay.
And then there's also bars. We used bar a lot. BARR.
Yes. I don't know why none of those other ones came to my mind. PSI obviously should have thought of because of tires. Yeah. And bars I should have thought of because of coffee. That's what, like, they measure pressure for like a espresso machine in bars.
Oh, interesting.
So both those should have come to mind for me. I think the idea of a gas.
Sciencey one.
Right. And a gas captured and contained somewhere. That, PSI should come to mind. But bars, I think of like, I'm putting pressure on something.
Yes.
So atmosphere, I don't know, for some reason seemed different than that, but it makes sense. You could measure those in similar ways or whatever.
They're all essentially measuring the same thing, just the same way Fahrenheit and Celsius are measuring the same thing.
Okay.
Or like miles and meters are both measuring distance. They're all measuring pressure, but they just have different methods of measuring pressure.
Right. And I guess they probably have different, like one unit would be different sizes too.
Right.
Like obviously that's one of the benefits people have, or like, Celsius over Fahrenheit instead or whatever, Like 1 degree of Celsius is actually larger than a degree of Fahrenheit.
Yeah.
Or stuff like that.
With a quick Google, I found that 1 standard atmosphere is equal to 14 psi. So yeah, they're different basic units. I don't know if that means very much to people, but
well, that's why we have to put more air in our tires. We can't just have 14 psi and our tires just like leave my tire outside for a little bit, let it fill with 14 psi. Like that's not gonna be enough.
What tire pressures do tires normally need to have? I don't have that off the top of my head.
32 is like, I think our car, or at least the one set of the wheels is 32.
Yeah.
But that's just off the top of my head.
That's double atmospheric pressure.
Yeah.
Roughly.
Yeah.
So there you go. That's a little side note. That was a fun side note.
Yeah, little tangent. Sorry. I mean, it ended up panning out, I guess, but
that's okay. I think that was fun. So, and that's basically it. That's how pop rocks work.
Okay.
Except there is more chemistry to it than just gas molecules trying to expand to fill a container.
Okay.
How do you think does the sugar dissolve?
Because of our saliva?
Right. But what would allow our saliva to interact with sugar molecules? So let's say, I know there's other stuff in saliva. Let's get rid of all the other stuff in saliva and just focus on the water in saliva.
Right.
How does water interact with sugar? Yeah, say it.
I mean, the water dissolves the sugar.
Yeah.
Do you want me to say more than that?
I do want you to say.
Okay.
If you can't, it's okay, but I think you have the answer for this already. So what have you learned about how 2 molecules interact with each other? Like, how is the water molecule interacting with a sugar molecule?
Seems like you know exactly what you want me to say, and I'm like, oh man, there's so many things I could pull out of my brain from different episodes, and none of them could be right.
I think you do know the right answer. I just think you haven't applied it in this new context yet.
Okay, so one thing I could think of is that it could, just the bonds could change a lot. So, like, either the water could start breaking down parts of the sugar, or it could start exchanging molecules or electrons between each other or something like that.
Okay, so that would be a chemical reaction, but that doesn't happen because sugar stays sugar even when it dissolves.
Okay.
That's a good guess.
Okay, I got this. Okay. So it's just that the molecules of sugar are able to spread out. So they're very close together, right? Packed in, and they're in a crystalline situation.
Yes.
So is it that because of the water, it's able to, that's why it changes form? It's not solid anymore. It slowly becomes a liquid because the sugar molecules stay liquid. They stay sugar, but they're spreading apart.
You're so close. Okay.
Ugh.
The sugar molecules, they do move around from being all in one crystalline state, but they're not changing to a liquid. They're getting dissolved, which means the water molecules are surrounding them.
Okay.
But we learned one type of force that describes how 2 molecules interact. A series of forces that describe how molecules interact.
Oh, intermolecular?
Yes.
Is there a specific one you want me to say?
No, I just wanted you to bring up intermolecular forces.
Okay. Man.
That's a bad teaching technique. Usually you should ask a wide range question so that students can say a lot.
Yeah.
But we talk about intermolecular forces so much, I thought you would have it on the top of your brain.
Well, what's funny is that, like, I think because we talk about it so much, it doesn't occur to me to be like the answer to a question. It's like, it is so much a part of everything we do. Mm-hmm. So I was like, oh, she wants me to be like specific, like, okay, well, what's happening at the molecular level? I don't know. I'm going to guess. But
I liked, though, that you were thinking about the molecular level. I think that is important.
So anyway, yes, I probably could have easily gotten that. I just was thinking too hard or something.
Yeah, you overshot.
Yeah.
You were being too impressive.
Yeah. Oh, yeah. Oh, yeah. Very impressive.
So intermolecular forces allows the water molecules to interact with the sugar to actually dissolve that sugar and take the individual sugar molecules, and they'll spread all out in the water and our saliva.
Got it.
I'm sure there's also other things in our saliva that are happening, like enzymes and stuff.
Yeah.
But you can also see Pop Rocks pop in water.
Right. Okay.
And then there's another thing that exists in our mouths that makes this dissolving happen more rapidly, that allows the CO2s to break out, or the CO2 molecules to break out.
Okay.
So if our mouths were cold when we put the Pop Rocks in, you would have less energy being put into the molecules.
Right.
So the heat of our mouths not only makes it easier for the sugar to dissolve in the water of our saliva, but it also puts energy into those carbon dioxide molecules, so they are moving around more.
Right.
So they're more ready to break out of their sugary cells than they would be if it was in a cold temperature.
Right.
So our mouths not only give the water that dissolves the sugar so that the barrier for the CO2 to break out is thinner and thinner.
Yeah.
But it also puts heat into the way these molecules are interacting to give them more energy so that everything happens faster.
Got it. Right.
So that's your 3-in-1 chemistry lesson.
Okay. Wow. There's a lot more to Pop Rocks than I thought. I don't know what I would have expected, but yeah.
I didn't really think about what they were either. I kind of assumed it would have been a acid-base reaction to produce the chemistry, like to produce the carbon dioxide on the spot.
Uh-huh.
I didn't think about the fact that they could just have put the carbon dioxide in.
Yeah.
Because a lot of things are carbon dioxide. Like if you mix baking powder or baking soda and vinegar, baking powder is a base and an acid already mixed in.
Yeah.
All those things that release bubbles, bath bombs, a lot of stuff we've talked about before just releases bubbles.
Yeah.
So I think I assumed there was some, when we put it in our mouths, the liquid allowed some acid base reaction to happen, and that was the pop.
I see. Yeah. That would make sense too. Yeah.
Okay, so that's your 3-in-1 chemistry lesson, and I want you to try and give it back to me.
Okay.
And then I'm going to, give our listeners and you an at-home experiment you can do with Pop Rocks.
Okay, sweet.
And 2, I'm going to talk about one other link to a previous episode we've talked about that could play into how Pop Rocks interact with our bodies.
Okay, sweet.
Okay.
So the first thing that we talked about is that there is carbon dioxide gas that has been trapped inside these little Pop Rocks on purpose.
Yes.
And obviously that carbon dioxide gas wants to get out, especially because it has been very pressurized. They put a lot of gas in an amount of space that the gas wants more room.
Yes.
As soon as
molecules.
Yes.
Yeah.
And so all these molecules of carbon dioxide are packed in there, and they are waiting for a chance to bust out.
Yes.
But before we put these little Pop Rocks in our mouths, they do not yet have enough pressure to break out.
Right.
Of how strong the Pop Rock is.
Yeah, the sugar is a strong cage.
One of the images that came to mind for me, I liked your fish in a net thing a lot. I was thinking about, I went grocery shopping last night and came back. I was thinking about how treacherous it can sometimes be when you are bringing a lot of groceries in and some bags are very, very full of stuff.
That's a good one.
Every bag of groceries, if you have either paper or plastic, or if you use your own, obviously if you have reusable shopping bags, this is not going to be as much of a problem for you. But for either paper or plastic, you can get a lot of groceries in some of those, but the risk starts to become higher and higher of those groceries busting free from the constraints of the bag.
Yeah, definitely.
And that's always sad, especially when it ends up being the apples or something like that fall out.
Or the glass, like olive jar container, olive oil container.
Yeah. So in the Pop Rocks, as we put the Pop Rocks in our mouths and we start to dissolve away the sugar that the carbon dioxide is trapped inside, the walls of what is containing them become thinner and thinner.
Yes.
And it gets more and more possible, more and more easy for them to be able to eventually break out.
Yep.
And once it gets thin enough and they do that, it feels to us very much like something just popped.
Yep.
even though it's not really like a chemical reaction kind of thing that happened. It was just already in there.
Yes.
And got a chance to release itself.
Mm-hmm.
And then the other thing that's happening is the second thing the dissolving, you said?
Yes. I talked about also the dissolving.
Okay. So the reason that our saliva, there's probably other things in our saliva, but one of the basic things would just be that there is water in our saliva, and it is able to dissolve the sugar and start pulling it apart and away and stuff because of intermolecular forces.
That's right. Well, I do want to ask in your analogy of your bags, intermolecular forces. I don't think I did a quick review of intermolecular forces, but it's just the way that the electrons in two different molecules allow the two molecules to interact.
Right, right.
And we did a lot of episodes about that early on, so you can go back and listen to some of those. But what in your analogy is pulling apart your grocery sack? Is there a nefarious creature below spreading it?
That could easily be. I mean, that could be one of our dogs.
Or a child.
Or a child.
If it's a brown paper bag and it gets wet.
Yes. Oh, yeah.
That's a good, okay.
100%. Like a lot of times I want to put frozen stuff in the brown paper bags, which it's always confused me a little bit because of the fact that in the car ride, the frozen stuff is getting meltier.
Yep.
I realize some of it's because of the size of the bags. You can fit a lot in there.
Oh, yeah.
But then when you get home and the paper bags are wet.
Yeah.
And way more prone.
That is a good
falling
analogy.
apart.
If you have a brown paper bag busting full and there's condensation happening.
Yeah. Yeah. Yeah, there we go. That's it.
It's slowly defying the integrity of the situation.
Yes. I had to not think about that before, but yeah, now it makes sense.
That's a good one.
I'm glad
and it's water in both cases.
Yeah. Exactly. Perfect.
It's probably very similar at the molecular level, what the water is doing in both of them.
And then the third thing you said that we've talked about in a bunch of other episodes too is just that heat, the increased energy that comes with heat often speeds up reactions of any kind.
It just makes molecules move around more.
They move around more. And that would be, obviously our mouths are usually warmer than the outside of our mouths, unless you are in a super hot place, in which case I feel for you.
Yikes.
And so we're doing a lot of things there. It's like we're introducing water that starts to dissolve the sugar, while at the same time introducing more heat than they had. So it's all happening faster.
Yes.
But it still could happen if you just put room temp water, put the Pop Rocks in there. It would still probably happen. It just might be slower.
Yes. So I think that was a great analogy. One thing is that the heat makes the carbon dioxide molecules move more.
Oh, yeah.
Which basically puts more pressure. So similar to when it got cold, our air pressure in our tires goes down. When it heats up, the air pressure goes back up.
Okay, so would it speed up? It would usually, we've also talked about like water temperature being higher being better for dissolving stuff.
Yes, so it does.
It's two things.
Yes.
It's increasing the pressure of the gas.
Yes.
The CO2 that's trapped in there. And increasing the speed at which and the amount of which sugar can dissolve into the warm water in our mouth, so we call saliva.
Yes, absolutely.
Okay, that makes sense.
Nice. Okay, so and that brings us beautifully into a chemistry experiment you can do with Pop Rocks. So if you have two different sets of Pop Rocks, or you can just split them into two evenly.
Okay.
You can put some Pop Rocks into warm water and some into very cool water, like maybe water straight out of the refrigerator, and compare the rates at which they pop.
Okay.
That would be a fun experiment, especially for kids.
Yeah, definitely.
And ask yourself, okay, why is this one happening faster? Whatever. I haven't done this.
Yeah.
I found a very similar reaction on the American Chemical Society website a very similar experiment where they did that. And I included the link in our references, but I really want to do that now.
Nice.
That sounds fun.
Yeah, definitely.
I have a hard craving for Pop Rocks now. The other fun fact about this is we have CO2 detectors on our tongue. We talked about that way back on the why does carbonated water taste weird episode or something. Yeah. We talked, my brother requested it, I remember.
Does carbonation have a taste? I think
yes, that's what it was. Yes.
Like
So it's possible that this whole experience is made more enjoyable by those CO2 detectors on our tongue.
Interesting.
I feel like I don't know for sure, and I'm sure people have not looked into that.
Yeah.
But I'm assuming that adds to the sensation. If we're feeling the popping of the rock literally breaking open, and we're feeling the sensation of CO2 on our tongue. So that was my tidbit, but I haven't found references for that. That's just what I assume.
Yeah, interesting.
Those are two fun things for you to take away after our chemistry lesson.
Yeah, there's a few callbacks to other episodes in this. Like, it happens a lot, obviously, but this one seems like it's got several that are, at first glance, might not seem related. I mean, the carbon dioxide one definitely seems related, but we've talked about intermolecular forces tons. We've talked about things dissolving and other things tons. Heat.
Chemistry is all related.
Yeah. Weird. We discovered that just now. Like, you guys didn't realize this, but like, it's all related.
It's all related.
You heard it here first.
I didn't hear it here first. I don't want my my chemistry professors from grad school to be like, you heard it here first?
Yeah.
You just now got it?
Yeah.
But Jam heard it here first.
Yeah.
Okay, so great job. That was a fun episode.
Yeah, that was very interesting. I liked that one a lot.
Is there anything else fun that's happened to you lately that you want to talk about besides how much fun this Pop Rocks episode was?
Ooh, man, how that's so tough. What could be more fun than this Pop Rocks episode? Okay, so I have something fun, sort of, to share about that kind of relates to our podcast, a previous topic. So you and I were both very affected by the Teflon / cast iron.
Oh my gosh, yeah.
Episodes. We've talked about it a bunch of times. I've somehow found a way to bring it up a lot in my like fun thing from the week or whatever. So
you really took it to heart, you know?
I really did. And so the other day I was at the store and there was steak that was like on sale quite a bit.
Mm-hmm.
And I like rarely ever eat it. I'm not against it or whatever, but just going to a nice steakhouse, something that my wife and I just don't do very often or whatever.
Yeah, you guys go to Asian food places most often.
We do both appreciate good steak, but you know, good steak, high price, that kind of stuff.
Right.
So I was like, why not? And so we bought some steak and I looked up some really good like cast iron steak recipes. And by recipe, I mean, it's not like it's, you know, crazy, but I've never tried to make steak at home. So just bear with me. I'm not trying to reinvent the wheel here. I was discovering the wheel for the first time. All you guys already out there.
Yeah, Mason and I only cook steak on cast iron and usually at home. We're like, we could probably do it better.
I've never tried to make grill steak on my own.
How
ever.
Interesting.
Yeah.
I mean, it is really good on a good old fashioned grill.
Yeah. And I have one of my old roommates would do that on a grill.
Mm-hmm.
But the tough thing is that it, at least to me, seemed pretty hit or miss.
Yeah.
He messed it up sometimes.
It's easier with a gas grill that's more consistent. If you can kind of get where it goes on the grill down. Yeah.
And so we made steak, cooked steak, grilled steak, whatever you want to say, in our cast iron pans. And it was so good.
Yeah.
So dang good. And I just found a super simple like recipes, like salt rub kind of thing. Leave it in the fridge for a day or so. And it was really fun. And also, you know, my wife and I don't do fancy stuff at all very often.
Yeah.
It's like, whoa, we're having steak?
I know. Yeah, it makes a regular day fancy. A lot of times for holidays, that's our go-to. We're like, it's, you know, a bank holiday. We're off work on a Monday.
Mm-hmm.
Let's have steak for dinner.
Nice.
Our two go-tos are French toast for breakfast or steak for dinner.
Nice. And then we made some really good, like we love Brussels sprouts a lot and have a very specific recipe we love to do. But we did that also.
Love Brussies.
And so it was like even more special meal.
So fancy.
So
did you have a good potato with it? Like a nice potato wedge or some kind of something?
We did. We have this microwave I talked about before.
Oh,
that's like a 4-in-1.
Someone did reach out and ask us about the type of microwave it was.
It's kind of nuts. So it's like got a broiler, a convection oven, and an air fryer all in there, which I realize that's probably a lot of the same technology, but it has very different settings for things you do. And it calls it a 4-in-1. Okay, that's their marketing, not me. Anyway, we baked potatoes in there.
Nice.
And what was crazy too is it was so fast.
Yeah.
It was incredible. And anyway, so that's kind of my thing. We had a fancy meal.
That's a good one.
Some of you guys are like, we do that all the time, but We don't. And we have a kid. And so anything.
So it's hard to do fancier things.
Yeah. Anything fancy, it also is cheap, is
Yeah.
like, wow, that makes for a fun week.
Yeah, that really does.
That's all I need.
Well, I have a very like only kid free type people are going to do this. So mine's kind of similar.
Okay.
I guess in that it was a fun, spontaneous kind of fancy thing.
Nice.
So I went to Austin on a work trip a while back and it was so fun. And I was telling Mason about all the good food I ate.
Uh-huh.
And I love Indian food. And there's a not high concentration of that in Denton.
Yeah.
And there's so much good in Austin. And I was just so excited. So I convinced him that we should take a day trip
Oh, nice.
to Austin.
Uh-huh.
And we could thrift and do all these things. So that's been on the, hey, let's do this
Yeah.
idea for a while. And then I was on TikTok, which shout out, I'm at Organic Melissa on TikTok if you want to follow me. But I was on TikTok and I found an Austin photographer who happened to be needing models to come and do a downtown like South Congress photo walk.
Whoa.
And I said, hey, we will get our pictures taken.
Yeah.
And so we did, and it was really fun. So we got our pictures taken from this on this downtown South Congress walk. So we went to all those cool murals in Austin, which I've been to Austin a lot. I had never seen South Congress because I don't like trying to park in hard places.
Right.
So, but that was really fun and worth it. And she was really cool. She's, I think, at Emily Makes Stuff. That's her business name. I'll tag her in some pictures I can post that she took.
Yeah.
And she did a really good job. And we had so much fun.
Nice. Dude, that's awesome. That sounds super fun.
Yeah.
I had no idea you guys did that.
It was so spontaneous. We just kind of took off randomly one day. We were back in time for... we had church stuff on Sunday. We were back in time for that.
Yeah.
We had good food. We have this beautiful city with really delicious food and cool cultural stuff just a few hours away. And we wanted to take advantage.
That's awesome. Very cool.
So that was a really good time. That's what my fun thing was.
Yeah.
So now if you're in Denton, Catherine Nicole Photography. If you're in Southern DFW, B Dallas Creations.
Uh-huh.
And if you're in Austin, Emily Makes Stuff.
Nice.
We've got a photographer for you all over Texas.
Yeah.
So that was our fun adventure. Almost as fun as this Pop Rocks episode.
Which we have Katie J, our friend and listener, to thank for that idea and suggesting it. And if you out there have a question in your everyday life you've wondered about, like, is this chemistry? And if so, how? And if how, when? And if when, could someone tell me? And that's why we are here. So please send your ideas or questions or thoughts to us on Gmail, Twitter, Instagram, or Facebook at Chem for Your Life. That's Chem, FOR, Your Life, to share your thoughts and ideas with us. If you'd like to help us keep our show going and contribute to cover the cost of making it, go to ko-fi.com/chemforyourlife. And the link is also in our show notes to donate the cost of a cup of coffee to help keep our show going. And if you're not able to donate, you can still help us by subscribing on your favorite podcast app and rating and writing a review on Apple Podcasts. That also helps us to share chemistry with even more people.
This episode of Chemistry for Your Life was created by Melissa Collini and Jam Robinson. References for this episode can be found in our show notes or on our website. Jam Robinson is our producer, and we'd like to give a special thanks to A. Hefner and V. Garza, who reviewed this episode.